Good afternoon, class. Here's practice test number 4, module 4, chapters 8 and 9. And we are covering chapter 9, inferences from two samples. Could somebody read the question, please?
Among 843 smoking employees of hospitals with the smoking ban, 56 quit smoking 1 year after the ban. Among 703 smoking employees from workplaces without the smoking ban, 27 quit smoking a year after the ban. Is there a significant difference between the two proportions? Use a 0.01 significance level.
Perfect. So what is it that we are dealing with? We are dealing with a binomial distribution, BD, because there are two outcomes. So what are the given information? I can't emphasize writing this. I can't emphasize how important it is. BD, N1 is 843. X sub 1 is 56. N2 is 703. And X sub 2 is 27. This represents alpha. So this is the given. Now we do the 4-step test of hypothesis. The 4-step test of hypothesis. And that requires knowledge of some formulas. So the formulas I want to remind you. We have something called P bar. We pull the proportions is X sub 1 plus X sub 2 over N sub 1 plus N sub 2. Again, all of these formulas are given to you in the formula sheet. The z-score is similar to the z-score for a binomial distribution with one sample. It's similar. P1 hat minus P2 hat. Square root of. This is P bar Q bar over N1 plus P bar Q bar over N sub 2. Those are the formulas available to you in the formula sheet. So the very first thing we need to calculate is P1 hat. Everybody remembers is X sub 1 over N sub 1. Since we wrote it here, we can easily calculate that. 56 over 843. The next one is P2 hat, X sub 2 over N sub 2. Again, the given, plug in, X sub 2 over N sub 2 is 27 over 703. Then we want to calculate the P bar. Again, we have the formula, X sub 1 plus X sub 2. That means 56 plus 27 over N sub 1 plus N sub 2. That means 843 plus 703. And that's P bar. So those are some calculations we need to do. As you remember, of course, in this case, we have a Q bar. As you remember, Q is in general 1 minus P. So Q bar must be 1 minus P bar. Q bar is 1 minus P bar. So let's write the steps. The very first step, P1 minus P2 is 0. H1, P1 minus P2 is not equal to 0, which makes it a two-tailed test, which makes it a claim. Why is that? Take a look. Is there a significance difference? When they're asking for that, it's not asking for less than or greater than, then it's not equal to. Now, this sometimes we might write it as follows. P1 equals P2. P1 is not equal to P2. Those are the same concept. So that's the first step. H0, H1. With the H1 goes the inequality, less than, greater than. The tail goes with that. You write the tail, in this case is two-tailed test. The claim goes either with H0 or H1. It's not always with H1. Now, the second step is test statistic. And the test statistic uses this formula. And because we want to use this formula, we did all these calculations. P1 hat, P2 hat, over the square root of P bar Q bar over N1. We did all of these calculations, so it helps us here. You put it into a calculator and you get the test statistic Z equals 2.4319. The critical value, CV, comes from the choice of alpha, which is 0.01. And this is z-score because binomial distribution gets approximated by normal distribution, and it's always the z-score. And it gives you plus minus 2.575 from the table. So if you do the graph, and that's extremely important that you do the graph. Here's a graph. We have minus 2.575 here, plus 2.575 here. And here's your test statistic that is way into the non-rejection region in between. The two tails are the critical regions or the rejection regions. This number, 2.4319, is somewhere in between. So don't reject or fail to reject the H0. So we don't reject H0. What are we rejecting? H1. Therefore, we are rejecting the claim. Rejecting the claim means the claim becomes false. So I can't emphasize this enough that this will result in the first part of the decision making only. So everything is about H0. After that, you expand for the claim becomes false. There is not a significant difference between the two proportions. So just you reword that. There is or there is not. In this case, there is not. What if we were to use technology? We use the two proportion z-test. Two proportion z-test. What do we put in? X sub 1, n sub 1, x sub 2, n sub 2. That's why symbolically it helps you put it in pretty fast. And which one of those do you choose? We said not equal. You choose this one because you can choose less than, greater than, or that one. When you do the calculation, it gives you some answers. What are those? I want you to see that. First and foremost, P1 hat is calculated here. We did it here. This has more decimals. P2 hat is calculated here. And we have it here with, of course, more decimals. What is this one? P bar. We have it here. Again, with more decimals. Now, what is this one? This one, which says P, is the P value. And remember, the P value in this case is 0.149277. It continues indefinitely. If you stop here, 0.149, you compare it to the choice of alpha. It's either smaller or larger. Because it's larger than that, we have the same decision, meaning fail to reject the known hypothesis. Whether we do it through technology or not, we have to write the steps. We need to understand what's going on. Now we're going to continue with the same question, and in part B, we're going to construct a 99% confidence interval for the difference between the two proportions. And remember, everything from here is from the previous page, the given, the P1 hat, P2 hat, P bar, everything that we have calculated, and this graph from the previous page as well. By the way, speaking of the p-value, I want to make sure everybody understands the p-value would be this area times 2. This area times 2, y times 2, because this was a two-tailed test. So the area to the right of test statistic, y to the right of test statistic, because the test statistic had a positive value. So that one times 2. Again, y times 2, because we have a two-tailed test. Now, so we have all those information here, and we want to find the confidence interval. First of all, 99% confidence interval in the middle. That means the two tails are 1% or 0.01 divided by 2, or 0.005 each one, 0.005. And the z-value that we found in the previous step works out the same here. And that's why the confidence interval is equivalent to this traditional method. So first, some of the formulas. Very similar to one sample. If you recall, the one sample was P bar plus minus E. P hat plus minus E. This is P1 bar minus P2 bar. And now we add and subtract E. Now what is E? Z alpha over 2 square root of P1 hat Q1 hat over N sub 1 plus P2 hat Q2 hat over N sub 2. It's a more complicated formula, however, you have it in your formulation. Now we have P1 hat, we have P2 hat, and of course Q1 hat is 1 minus those, and so Q2 hat. And the Z comes from the previous page. We had 2.57, remember that? The critical values, because that corresponded to alpha of 1% for both sides. So we have everything we plug in. This is the Z from the previous page. This is the P1 hat from the previous page. N sub 1, P2 hat, N sub 2. This one is calculated. This is, again, this is 1 minus P1 hat. This is 1 minus P2 hat. You do the math, you end up with the value of E. So you simplify this one, you simplify this one, you add them up, you take a root, you multiply by 2.575, you get this. And now we are going to go with P1 hat minus P2 hat, which means subtract this one from this first. Subtract this one from this one. And now this number must be subtracted from this and added to this according to this formula. Please understand, this is the P1 hat minus P2 hat, this one, and this one is the E. So subtract this number from this and add. So I'm assuming we have no problem with the calculation. Now, what is the meaning of it? This is important to understand. Because the confidence interval limits contain 0, notice, when we go from negative to positive, that means it contains 0. That's how we know that. If it goes from negative to negative, doesn't contain 0. If it goes from positive to positive, doesn't. But it goes from negative to positive, it does contain 0. There is not a significant difference between the two proportions. Fail to reject the null hypothesis. Because it contains 0, that means in essence P1 minus P2 could be equal to 0. That means P1 could be equal to P2. That's the meaning. Doing it with the technology, confidence interval 2 proportion. So we plug in X sub 1, N sub 1, X sub 2, N sub 2. This is 2 proportion Z interval. Confidence level of 0.99 or 99%. It gives you this answer. Again, P1 hat, P2 hat, N1, N2 are given. Also, here's the confidence interval. Take a look at this. First, I want to look at the right side. Look at the right side, 0.05695. Now, of course, why is there a difference? Because they do use more decimals than we do. All of these calculations, they use more decimals. Including the Z score, the Z value of 2.575. So it will be off by a little bit. And what is this one? It's negative 9 times 10 to the power of negative 4. And you can change that to this is a scientific notation. This number is negative 9 times 10 to the power of negative 4, which means the decimal is here. You move it this way 4 places. Becomes this value. As you can see, this value versus this value. If I stop here, I have to change the 8 to 9. They are identical within 4 decimals. All right. This one is the same as this one, as you can see. Could somebody read this, please?
Company A claims that its yogurt cups contain on average fewer calories than that of a competitor. A sample of 50 such yogurt cups of Company A produced an average of 141 calories per cup with a standard deviation of 5.4 calories. A sample of 40 yogurt cups of a rival Company B produced an average of 144 calories per cup with a standard deviation of 6.3 calories. A. If the calories of the yogurt cups for Company A and Company B have different variances, use a 0.01 significance level to test the claim.
Perfect. So first, we want to write the given and we want to write it symbolically. So N, X, S. So for example, N1 is 50. X1 bar, because it's the average, X1 bar is 141. Standard deviation, and all of them pertain to those 50, that's why. And this one is S, we're gonna call it S sub 1. Then this would be N sub 2. This would be X sub 2 bar, and this would be S sub 2. So we write them in this manner. So it's extremely important to understand the given symbolically, and of course, we know this is alpha. Now, we're going to repeat the same 4 steps. H0 mu1 equals mu2. H1 mu1 is less than mu2. And that's the claim, and that's the left tail test. Why is that the case? Company A claims that its yogurt cups contain, on average, fewer calories. Fewer. That means less than. By the way, we may write mu1 minus mu2 equal to 0. And over here, mu1 minus mu2 less than 0. So both of them are acceptable. So depending on how they write it, they mean the same thing. The next step is to calculate the test statistics. So reminding you of the formula sheet giving us t equals x1 bar minus x2 bar over the square root of s1 squared over n1 plus s2 squared over n2. See, now this is really helpful. Plug in. I can't emphasize the importance of writing the given symbolically. You plug in. By the way, this one, after that, we have minus mu1 minus mu2, and that's always comes from h0, which is 0, so you don't have to worry about that. The actual formula in some text, the numerator is x1 bar minus x2 bar minus mu1 minus mu2. Because in some instances, not in the course, but out there, this may be a specific number. This is mu sub 2. This mu sub 2. In any event, and it's always 0. So now you do the math, and it gives you the test. This is statistic of negative 2.3901. Now, the critical value alpha is 0.01. And in the text, when we assume different variances, we take the smaller of the 2 degrees of freedom. N1 minus 1 is 49, N2 minus 1 is 39, and we use 39. This is what the text does. If we use the technology, it will be different. I will discuss that in a moment. And so 40 minus 1 is 39, and the t-value is negative 2.426. And we always do the drawing. It's truly helpful to see the location of the critical value versus the test statistic. So in this case, the critical value is negative 2.426, and this area, this alpha is 0.01. Test statistic, negative 2.3901 is a little bit larger than that. It's way into the non-rejection region. None of those values are to scale. The point is it's in the non-rejection region. This is the tail and the rejection region. This is a non-rejection region. Therefore, don't reject H0 or fail to reject H0. And if you don't reject H0, you're rejecting H1 or the claim. So don't reject H0 or fail to reject H0. So what are you rejecting? H1. So claim is being rejected, meaning the claim becomes false. There is not enough evidence to support the claim that company A's yogurt cups contain on average less calories than that of its competitors. So again, this is if you don't use the technology, the numbers will be different, and that's fine as long as you show your steps. Now we're going to look at the same thing, and we want to go with the p-value. And we are writing everything from the previous page. It's the same question part. We calculate the p-value for the test of previous part and make a decision. Is this decision in agreement with the previous one? And again, we have all of that. And remember, to find the p-value in essence, you want, this is your test statistic. And it's a one-tail test. You want this area. And the concept is now you area this, you compare this alpha, which is the area, compared to the p-value, which is a different area. And obviously, the p-value will be larger and you get the same decision. But if you wanted to find it, how do you do that? It's a left tail test, area to the left of test statistic, this area. Maybe I go with a different color, actually, this area. Versus the green area. That's the concept. And degrees of freedom is 39. So for 39, this number, negative 2.3901, we want to locate it here. And because of the limitation of the table, you can first look for the positive one, 2.3901 here doesn't exist. But I hope you see that the positive value is somewhere between these two numbers. Therefore, the negative number is between the two numbers negated. So this is the number that we are looking for. What number are we looking for here? Positive 2.3901 is in between these two. So negative value is between the two negative. And the area is between these two as a result. So degrees of freedom is 39. Again, I'm showing you how to do it with the table. Test statistic of negative 2.3901 is between these two numbers. And so the area is between these two numbers. That means the p-value is between these two numbers, which is clearly larger than 0.01, alpha of 0.01. And we get to the same decision. Fail to reject the null hypothesis. Therefore, the claim is false. Decision is in agreement with the previous part. If we were to do it this way. Now, what happens if we do it with the technology? And I want you to pay attention to this. We are going to use two sample t-tests, and we're going to plug in the values. When we go with two sample t-tests, we go to stat and test, and we put in x1 bar, S is S1, N1, x2 bar, S2, N2 bar. You put all of them. And for, again, the tail, you decide to be two-tail, to deal with the two-tail test, left-tail test, or right-tail test. So in this case, it was a left-tail test, as you remember from the previous page. Mu1 was less than mu2. So with that being the case, when you do the calculation, it gives you the following information. So let's see what those informations are. You calculate the results are completely different since degrees of freedom has a different value. Take a look. Here's the complicated formula for degrees of freedom. It's a plus b quantity squared over a squared over n minus 1 plus b squared over n sub 2 minus 1. where A is S1 squared over N1 and B is S2 squared over N2. Okay? So the degrees of freedom that you see here, this is the degrees of freedom calculated using this formula, everybody. But for the text, we go with the different value, the smaller of the two. And here's the p-value here. So the p-value is 0.0096. If we stop here, the 6 doesn't change because next to it is 4. Now you compare it to alpha, this is less than alpha of 0.01, and you reject H0. It has a different result because the degrees of freedom is different. Since the difference between the two degrees of freedom, between this one, 39, and this one, 77, is a lot, they don't give us the same results. If they are fairly close, we end up with the same result. But as I mentioned, just show work, you have nothing to worry about. Now, we are looking at the same question. We want to find the 98% confidence interval for the difference between the two means. And I want to show you how fast and easy you can get to the answer. So again, the information from the previous page, N sub 1, X sub 1, so forth. T, this is the test statistic. And I wrote that, and I wrote that because there's a reason for it. We're going to use that. So this, everything comes from previous 2 pages. You want x1 bar minus x2 bar plus minus e. First of all, what is x1 bar minus x2 bar? Is the numerator of this. So this is already calculated. What about e? Let's write the formula for e. E is T alpha over 2 squared of S1 squared over N1 plus S2 squared over N2. I want you to take a look at this one. These two are the same. So this denominator, which is calculated here, we already have it here. So take a look. These two are identical. Again, I want to show you how to use the minimum amount of calculations. Remember the T from the previous page? We're going to put it here. Of course, we use a positive value because we're going to put plus minus. So we have the T from the previous page. We have this one also, which is the denominator here from the previous page. So take a look. Here's the T value, positive value. Here's the denominator of your test statistic. So this becomes a piece of cake to calculate. And now we know this is -3. So we are going to subtract this number from -3. We add to it also. I'm showing you where they come from. So this was -3, and add and subtract these two numbers, and you get -0.06045504 less than mu1 minus mu2 less than 0.04504. Again, the confidence interval limits does have the 0. Because the confidence interval limits contain 0, there is not a significant difference between the two, means fail to reject the null hypothesis. I hope you see the ones that we've done by hand, the p-value, the traditional method, and the confidence interval, they all result in the same thing, and they're supposed to. Now, if we go with the calculator, 2 sample t interval, and we put in the same information as the previous page. They're asking for x1 bar, S1, N1, x2 bar, so on and so forth, the confidence level of 98%. By the way, I want to discuss that before I continue. If you remember, alpha was a 0.01. And this was for a left tail test, or whether it's just in case one tail test. So if you were to translate it into 2 tail test, that makes it 0.02. That's why 0.01 alpha for 1 tail test, whether it's left tail or right tail, makes no difference, is the same as 98% confidence interval. If it was a 2 tail test, we would need a 99% confidence interval for it to be the same. So if this is 0.01. If you make up another 0.01 here in the middle, you have 98%. So again, put 0.01 here. Each tail has 0.01. So in the middle, we have 98%. That's why we have 98%. So we're going to continue with that calculator thing. It gives us the answer here. And more importantly, again, take a look at the degrees of freedom. The degrees of freedom is exactly what we got using a calculator previously for the p-value. And so those values are different. And notice both of them are negative. Calculated results are different since the degrees of freedom has a different value. Because the confidence interval limits are both negative and do not contain zero, there is a significant difference between the two means, reject the null hypothesis. So again, this works the same as the p-value when we use the calculator. They are in agreement using a calculator, as they are in agreement not using a calculator and going with the degrees of freedom 39, which is way different than the actual, which has been calculated. Now, we're going to look at the same question, but this time we are assuming equal variances. So if the calories of the yogurt cups for company A and company B have equal variances, repeat the previous questions. By the way, we can't assume that unless it has been mentioned that. We are going to use the same 4 steps of the test of hypothesis. We have those information. So the very first step is the same, H0 mu1 equals to mu2, and H1 mu1 is less than mu2. So the first step is the same. But what is the second step? Test statistic has a different formula. Here's the test statistic. T is x1 bar minus x2 bar over S sub p quantity squared over n1 plus S sub p quantity squared over n2, which is the pooled variances. So the pooled variance has this formula. It's a pretty complicated formula, but again, you have access to it. So what is S sub p squared? N1 minus 1 S1 squared plus N2 minus 1 S2 squared over N1 minus 1 plus N2 minus 1. They would be the same if you could add them up, divide by 2 if they have identical size, if N1 and N2 were equal. But anyways, so you calculate S sub p using this formula and using the table. 49 times 5.4 squared plus 39 times 6.3 squared over 49 plus 39 results in 33.8267. This is called the pooled variance. That's the terminology. The second step is now to calculate the test statistic using this formula. And we're going to use S sub p in each case. Using a calculator, we end up with this, negative 2.4316. And the next step is the critical value. Alpha is 0.01. Alpha hasn't changed. Degrees of freedom in this case is the sum of the degrees of freedom. So 50 minus 1 and 40 minus 1, they add up to 88. N1 minus 1 plus N2 minus 1. When we go with table, 88 is not in the table, so we can go with the closest number, which is 90. But again, if you use the technology, they do have the actual answer, but the answers are extremely close anyways. So when we use the table, we end up with negative 2.368. So we do the drawing, we put this one and compare it to the test statistic. So in this case, negative 2.368 with the alpha of 0.01 is somewhere here, and negative 2.4316 is smaller than that. It puts the test statistic way into the rejection region. Again, this tail is the rejection region. This is a non-rejection region. This is the critical value. Test statistic is smaller. Therefore, you are rejecting H0. And if you're rejecting H0, in essence, you're not rejecting H1. You're not rejecting the claim. The claim becomes true. So Reject H0 because the value of test statistic is inside the rejection region. The claim is true. Therefore, there is sufficient evidence to support the claim that company A's yogurt cups contain on average less calories than that of its competitors. Very straightforward. Same question, you're going to calculate the p-value. Same question. The p-value is this area because it's a left tail test, area to the left of the test statistic, which is negative 2.4316. Degrees of freedom is 90. So the t-value is between these two. And the area in one tail, again, limitation of a table, we don't have this value in there, but understand we are looking for the area to the left of that. Since we don't have it precisely in the table, we look at the number that is in between. You can look up the table. I didn't put the table here, but you can look it up. And so the p-value is between these two. And as you can see, for sure, the p-value would be less than 0.01. So we have the same decision, which is rejecting H0. What if we want to do this with technology? Now, by the way, as far as the technology is concerned, it's important to pay attention to this one. Previously, to this question, we would say no when you use technology TI. Now we say yes. The same thing, but we say yes. So what happens when we put yes? Take a look. You put yes, you do the calculation, and take a look at what's important. Degrees of freedom is what we have already, 88. The p-value is 0.0085, which is clearly less than alpha of 0.01. And we have the same decision. So the technology gives us the identical answer as we got. So the only difference is when you put it in over here, the answer to pulled would be yes. Everything else is the same. So the same thing that you put in there. Now, this is the difference. Now we're going to get the same question. We want to find the 98% confidence interval, and we're going to use basically the same formula, x1 bar minus x2 bar plus minus e. And this is the formula. Now take a look at the test statistic formula. I'm going to remind you. And look at the e, which means this number and this number must be identical. And therefore, you don't have to recalculate. It's just grab it from your previous calculation. As far as t is concerned, we had the t, so you put it here. Of course, you don't need the negative sign. So recall that the test statistic had this formula and this, so we are interested in this denominator. So what is the value of this one? T, this number, times this number. And the product of the two, okay, gives us 2.9216. I'm showing you all of this because if you're doing this by hand, you should know how to speed up your process and don't redo the same problem. Now we want x1 bar minus x2 bar. This is the numerator here, -3. So -3, add and subtract this number. And so mu1 is between minus 5.9216 and minus 0.0784. Both limits have the same sign. That's the idea, negative or positive. They both have the same sign, which means 0 is not included. Because the confidence interval limits do not contain 0, there is a significant difference between the two means. Reject the null hypothesis. Remember, the null hypothesis is the one that has the equality. The alternative hypothesis, H1 or H8, doesn't. It's either less than, greater than, or not equal. If we were to use the technology, we would use 2 sample T interval, and we would put all the information. And over here, fold again, pay attention to this. We put yes for this part. Take a look. This number, minus 5.923, this one becomes 2, minus 0.0766. Why are they slightly different? Because again, it uses 88 instead of 90. This would be different, and it uses more decimals. But nevertheless, both are negative, and they confirm the same decision we made. Could somebody read this question, please?
Test the claim that weights of male college students have a larger variance than female college students. Use a significance level of 0.05 and assume the populations are normal. A equals 0.05.
Perfect. So we are given the information symbolically. So it's n, x bar, s, so on and so forth. So what we are going to do, instead of n, we're going to call this n sub 1, x1 bar, and s1. So we can separate. And this one, n sub 2, x1, x2 bar, so on and so forth. And of course, alpha is 0.05. It's a normal distribution. So what are we doing? The very first step, I want you to see what's going on. There are 3 different ways of writing them. I'm going to write all 3. You don't have to write all 3 for your homework or the exam. Just follow, make sure you don't make a mistake. We may write sigma 1 squared equals sigma 2 squared for the first step, H0, or sigma 1 squared over sigma 2 squared equals 1, because if they are equal, the ratio is 1. Or we may write sigma 1 is equal to sigma 2. So this is the variance. This is the standard deviation. So one of those. If we use this one and larger, we are testing the claim that this is larger. So this is a right tail test. Then you say sigma 1 squared is larger than sigma 2 squared. That is the claim, and that's a right tail test. If you go this route, then this ratio is larger than 1. I hope you see why 1. If they are equal, the ratio is 1. If this is larger, the ratio is larger than 1. In this case, sigma 1 is equal to sigma 2. In this case, sigma 1 is larger than sigma 2. You don't write all of them. There are 3 different ways of writing. The next step is to find the test statistic, which is the easiest test statistic using f s1 squared over s2 squared. S1 is 28 squared, and S2 is 25. By the way, we choose this such that this becomes a number larger than 1 because of the limitation of the table known as the F distribution. We make sure the first group has a larger variance, a sample variance. So for example, if this group is given as the second group, you change it to the first group because S1 is larger than S2. This is how you calculate it. Again, by choice, the one with the larger S value is the first group for this one to work. And therefore, this number is always larger than 1. And therefore, it is always a right tail test. What about the critical value? Alpha is 0.05. We are dealing with the right tail test. So we have 2 degrees of freedom in the case of a F distribution. We have the degrees of freedom of a numerator. That means the first group. That means 31 minus 1, or 30. And we have degrees of freedom of the denominator. That means the second group. That means 29 minus 1, or 28. So we have F distribution, which is similar to chi-squared, it's skewed to the right. And you have different tables. In this case, alpha is 0.05. You have to make sure you choose the correct table. Alpha is 0.05 because they have tables with alpha being different. For example, alpha equals 0.01. So the very first thing you need, proper table, proper choice of alpha. And when you look at that, up here we have degrees of freedom for the numerator. In this case, you're looking for number 30. And the left column, right here, and again, I didn't have room. There are a bunch of numbers. You're looking for degrees of freedom, which is 28. So you locate that. You put those two together. And you read this number. That is the F 1.8687. Now, as you can see, for alpha of 0.05, F is 1.8687. This is your critical value. Now, this number, where does it fit? Remember, this goes from 0 to infinity, and this number is less than that, so somewhere here. It's way into the non-rejection region. Therefore, you fail to reject the null hypothesis. So, if you fail to reject the null hypothesis, that means you reject the alternative hypothesis. You reject the claim. The claim becomes false. So, fail to reject the null hypothesis because the value of test statistic falls in the non-rejection region here. The claim becomes false. Again, why is the claim false? Because you're not rejecting H0, you're rejecting H1. What does it mean? There is not sufficient evidence to support the claim that weights of male college students have a larger variance than female college students. How about technology? You use two sample F test and you input S sub 1, N sub 1, S sub 2, N sub 2, and you choose a tail. So we put S sub 1, N sub 1, S sub 2, N sub 2, and you choose the tail. In this case, is a right tail test. And again, don't forget, I'm going to emphasize this. Make sure the first group has a larger S. So if this was written at top, you use this one as the first group, the one with the larger S. When you do that, it gives you those values. So, number one, here's the test statistic that we calculated. Number two, the p-value is 0.274 and 6 in this case, which makes it larger. 0.27 if we stop here, 5. Larger than alpha. What was the choice of alpha? 0.05. Definitely larger than alpha. And that gives you the same decision. Same decision. Could somebody read this question, please? Go ahead, please. Last question, somebody read it, please.
Directional asymmetry, D8, is a phenomenon whereby in a population, one side of each organism is consistently larger than the other, i.e., left larger than right. An evolutionary biologist studying DA measures the length of the left and right wings of a sample of Drosophila, a type of flies, whose numbers are often called small fruit flies, collected from nature, and she gets this data. A, the researcher decides to perform a two-sample t-test to determine whether the mean wings differs between the left and right sides of these flights. What type of t-test will she do? A equals to 0.05. B, find the 95 confidence interval for the difference between the means.
Perfect. So the very first thing is we are looking at the same group, the left wing and the right wing. So we do what's called the paired t-test. And for the paired t-test, all we have to do, calculate the difference. Calculate the d or the difference between the length of the left wing and the right wing. And it doesn't matter which one you use as the first one, which one you use as the right one. Ultimately, the concept is the same. You can say 1.34 minus 1.26 and write it, or you write 1.26 minus 1.34 or write it. Just be consistent. Whatever is the first one, you keep it. If the left wing is the first one, always the left minus the right. If you want to do right minus the left, it's just as good. But all of them, not some of them, otherwise it will be wrong. Be consistent. So we're going to do left minus right, left minus right, 1.34 minus 1.26, 1 minus 1.28, 1.09 minus 1.36, and we make up a new column. So left, so we subtract, okay, left minus the right. That's what we did. Left minus the right. Again, as long as they're consistent, it doesn't matter. Now, we can put this into technology, TI, Excel, you name it, and calculate the average and the variance. First and foremost, N is 17. Now, we don't need this two anymore. We just deal with this. And so just the way that X bar was summation of X over N, D bar is summation of D over N. It's the same as X bar in essence. Just the way that we found S as X minus X bar, now it's D minus D bar. And if you want to use a calculator, here's how we do that. We want to enter this data. Stat edit, first you clear the list L1 and L2. And here's in L1, here's in L2, and we are interested in L1 minus L2, and we store it in L sub 3. And then we do the calculation, and it gives us the D bar, which is the same as X bar, S sub D, which is the same as S, and N, of course, we knew it was 17. So this comes from technology. You plug it in, you find it. And again, the fastest way is to put this one in L1, this one in L2, and then L1 minus L2, call it the D in L sub 3, the third list. Now, let's do the test of hypothesis. So this was the beginning of the course. So we are looking at the same question, and we are going to do the test with alpha of a 0.05. So mu sub D equals 0 for H0, and H1 mu sub D is not equal to 0. That's what we are checking. So that would be the claim, and it's a two-tailed test. We have collected it, and we are checking to see if that's the case. So two-tailed test. Now we want to calculate the test statistic. And I hope you remember the test statistic was X bar minus mu over S over square root of N for the T distribution, right? For the average, it's exactly the same thing. Instead of D bar, instead of X bar, we call it D bar. Now, in some texts, they use lowercase d. In some texts, they use uppercase. And I like to use both of them, just tell you, depending on the text. We are going to plug in. And by the way, this is always 0 coming from the H0 mu sub D is 0. Sometimes they don't even write that in the formula. So this is D bar with more decimals I put here. You do the math, and we end up with test statistic of negative 1.636. Now the next one is alpha is 0.05. Degrees of freedom is n minus 1. That means 17 minus 1 or 16. And the table gives us plus minus 2.120, or again, technology, whatever that you want to use. So let's always do the drawing to make a decision. When we do the drawing, it's a two-tailed test, alpha over 2, meaning 0.05 divided by 2 here, 0.05 divided by 2 here. And this is negative 2.12, this is positive 2.12. Here's our number. As you can see, our number, negative 1.636, the one that is calculated for test statistic, is somewhere in between, way into the non-rejection region. Do not reject H0 or fail to reject H0. Fail to reject H0. That means you're rejecting H1. That means you're rejecting the claim. That means the claim becomes false. Do not reject H0. The claim is false. There is not sufficient evidence to support the claim that the mean wing differs between the left and right side of these flies. So according to this, this is not true. Therefore, she cannot conclude that this population possesses DA, directional asymmetry, because the mean length of the wings on the left and right sides do not differ significantly, according to our work. Now, if we go with the technology, we can do the t-test, and you can put the information from L sub 3, which is L sub 1 minus L sub 2, and do the two-tailed test. You can try it with technology. Same question, we want to find a 95% confidence interval. It's the same question, we've done all the work, and now we want a 95% confidence interval, where D bar is given S sub T n. And so this is the confidence interval. 95% is right in the middle. And so the two tails are 5% divided by 2, or 0.025, and we have the same T. That means negative 2.12 for here, positive 2.12 for here. And now we need to calculate the, remember, X bar plus minus E, now it becomes D bar plus minus E. And with that being the case, if you recall, E was T, S over square root of N, the same thing works here, but this time we call it S sub D. And so this value is 2.120. Then S is this value, square root of 17. So this really helps here. We get 0.1174. And we are going to subtract this from D bar, and we are going to add this to the D bar. So mu sub D is between these two numbers. As you can see, one is negative, one is positive. Since 0 is contained in the interval, the decision is to not reject the null hypothesis, H0 mu sub D equals 0. And you can use this technology, the matched pair T interval. And you use L sub 3 because we put L sub 1 minus L sub 2 in L sub 3. Again, it's absolutely up to you which list you use. Here's the last question, everybody. Can somebody read this? Last question.
An ecologist is concerned with whether pollution entering part of a preserve area is compromising the health and growth of an endangered species of snake. To determine this, he decides to measure the length of the set of mature adults from the polluted area In an unpolluted area, the researcher decides to perform a two-sample t-test to determine whether the mean length of these snakes differs between these two areas, alpha equals 0.05.
Excellent. And the idea is that these are, applications in real world. And so we have the length measurement for unpolluted area. We have 15 of those. And for the polluted area, we have 17 of those. And we need to do the math. In order to do the math for this sample, we want to calculate the standard deviation, the mean, and the sample size. Obviously, it's 15, and this one, the sample size is 17. So we input that into Excel, a TI, and we let that be calculated by technology. So, and we are going to assume different variances because it has to be mentioned otherwise. So when we put this into a calculator, we have the standard deviation with a bunch of decimals. For the first group, for the second group, we have the mean for the first group, the second group, and we have the size. So this would be S1, S2, X1 bar, X2 bar, N1, N2, just as an example, if we were to write them down. So maybe so this would be S1, S2, X1 bar, X2 bar, N2, N1. That's the concept. And T is X1 bar minus X2 bar over the square root of S1 squared over N1 plus S2 squared over N2. So let's do the math. And the very first step, mu sub 1 is equal to mu sub 2, and mu sub H1, mu sub 1 is not equal to mu sub 2, and that is the claim, and that's a two-tailed test. The idea is that the researcher wants to do what? To determine whether the mean length of these snakes differs. It doesn't say whether it's less, more, just are they different? That's why it makes it the two-tailed test. By the way, normally they use alpha equals 0.05 anyways, unless otherwise mentioned in basic research. The second step is to calculate this test statistic using the formula. That's why we've done this. X1 bar minus X2 bar over the square root of S1 squared over N1 plus S2 squared over N2. I didn't use as many decimals here. It's hard to fit it there. And when you calculate it, although when you do the calculation, you really do the rounding at the end. So 2.8022. The critical value, alpha is 0.05. Degrees of freedom is the smaller of the two. In this case, it's 15 minus 1, which is 14, 17 minus 1, which is 16. So we choose 14. Again, if you're going with the text. And T from the table becomes plus minus 2.145. Now we do the drawing. We put minus 2.145, positive 2.145, and where does this end? Notice we have a negative 2.145 and positive 2.145, and this number ends up being in the right tail, 2.8022, so that it's way into the rejection region. So that makes it reject H0. So if you're rejecting H0, you're not rejecting H1, you're not rejecting claim. That means the claim becomes true. And you're right, reject H0, the claim is true. There's enough evidence or sufficient evidence to support the claim that the mean length of these snakes differ in the snakes differs in these areas. It is larger in the unpolluted area since test statistic is positive. By the way, this part I'm adding to it. I want to make sure everybody understands what's going on. Normally we don't write this part, but clearly part A, B, C is understood. What's happening here, because this is positive and because we are rejecting H0, that means this is larger. If it were negative, that means it would be smaller. So it is larger in the unpolluted area since TS, test statistic, is positive. What if we use a calculator? Well, we put it in there, two sample t-test, and we put everything. And notice calculator gives us the different degrees of freedom. Take a look at the degrees of freedom we choose is 14 here, but over here, degrees of freedom is 29.39 because it uses a different formula. Remember the formula that I mentioned? And if you were to use table, you would go with number 29. You always round down in that case. And in that case, take a look at this one. This is the T that has been calculated here. And this is the p-value. And as you can see, the p-value is less than the choice of alpha, which is 0.05. Now, the CV, alpha is 0.05, degrees of freedom is 29 because you're going to round it down. And T is 2.045. This would be the critical value. This critical value is different than that if we were to go with degrees of freedom of 29. However, the p-value, which is 0.008, and we're going to change the 8 to 9 because next to it is 9, clearly is less than alpha of 0.05. We're going to reject H0, which means we're going to get to the same result as before. In this case, again, because the difference between the two degrees of freedom is not huge like before, the results are the same. And that's it.